Welcome to this presentation in the International Teleconference of Einstein's argument that quantum mechanics is not complete theory. My presentation is entitled Non-Unitary Lie Isotopic Lie Admissible Scattering Theories of Hadronic Mechanics for Deep Inelastic Electron-Positron and Electron-Proton Scattering. My name, the presenter, is Alex Animalu. My co-author of the presentation is Professor Ruggero M. Santilli. Now, let me briefly read the abstract. The non-unitary Lie isotopic and Lie admissible scattering theories of hadronic mechanics, also known as iso and GNO scattering theories, were first systematically studied by Santilli, references 1 to 3, and then by myself, Animalu, and Santilli, in references 4 to 8. Continue these studies by developing generalizations of the Feynman graph method for the computation of the S matrix, high-density scattering regions that cannot be consistently decomposed into a finite number of isolated point particles, according to various no decomposition theorems. More recently, by using Mu's nonlinear recursive differential equation, realization of Santilli's Lie admissible equations of motion to characterize the generalized structure functions. I, the presenter, have extended the results to the GNO scattering theory of deep inelastic scattering, thus irreversible electron-positron and electron-proton scattering processes, and obtain good results in theory and experiment and the GNO scattering data. So in this thing, we shall debate whether the high-energy scattering regions should be reinspected under the historical argument by Einstein, Podolsky, and Rosen that quantum mechanics is not a complete theory. In view of the apparent proof by Santilli, especially for high energy regions, suggesting the completion of the quantum mechanical scattering theory into the iso and GNO scattering theories of hadronic mechanics. Here the references. References 1 to 3, I've already said, are the foundations, theoretical foundation, experimental verification. And references 4 to 8 will be the concept, on non-unitary isotopic and Lie admissible scattering theories of hadronic mechanics. And then this presentation will be based on under the title we've given. It's a presentation that's published in African Journal of Physics, Volume 9 of 2016. The other refers to the argument 10 to 15, which I've already mentioned. Now, in the outline of the presentation, it consists of the background, explaining of problem and solutions, presentation of results, discussion, and conclusion. Now, on the background, let me quickly outline that this presentation is based on my personal knowledge of PM Dirac while I was a postgraduate student at Cavendish Lab, Cambridge, UK, during which time I had a brief meeting with R.P. Feynman, and subsequently through interaction with his former student, Robert Oakes, when I was a postgraduate research staff at the W.W. Hansen Lab, Stanford University, California, in the 1960s. Now and then I was involved in a chapel here in North Carolina as a theoretician In experimental measurement of angular distribution of photons from position annihilation with valence electrons in metals using Geno-dual model pseudo-potential theory. The foundation for comparison of numerical values predicted by the ISO and Geno-scattering theories of hadron mechanics with those of the conventional quantum mechanics were laid while I was working at MIT Lincoln Labs and later with Professor Santilli and others in a paper entitled Iso-Feynman Propagator and Isometrics of Hadronic Mechanics, published in Hadronic Journal 2008. I think I should quickly go through emphasize what the abstract is. Remember, the emphasis is on to lay Feynman space-time picture of quantum electrodynamics. That framework, a systematic method which is based on nonlinear, non-unitary transformation of Feynman propagator and S matrix into the corresponding isopropagator and iso-S matrix of hadronic mechanics. We're eliminating three bases of divergences in contemporary physical theories of quantum mechanics. Namely, one, the arbitrariness, the boundary conditions on the quantization volume, for normalization and associated differences in the quantum Bose-Einstein and Fermi-Dirac statistics. Two, the singularities, the Lorentz transformation, and the theorem of addition of two velocities. And three, the singularities arising from the assumption that particles are point-like, and interaction between them long-range character, which calls for arbitrary cutoff of divergent integrals. Now, let me begin by rehashing briefly a work on positron annihilation with electrons in metals. What is measured there, I'm not going to go into detail, but to say that essentially it measures the distribution of electrons in momentum in K-space, and the electrons we are talking, we have valence electrons, are usually on spherical, occupied states, bounded by a spherical Fermi surface. And it's really the shape of this Fermi surface, the distribution that we're after. And you can see when you take the cross section, a cross section will correspond to one of the experimental points, cross section area. So you can see there are three. This measurement was and theoretical study was made for C-axis yttrium crystal. And I published this when I was at MIT, my principal intermediate quantum theory of crystalline solids. You can see from the graph the experiments and the dip, and then the free electron, which is a spherical distribution, and the deviation which can become from Bragg planes and all that. So now I indicated that there are the objective and the problems. So I want to say isotope of Feynman diagram without divergences. That is the focus of what we want to do. So in phase quantization, we have to tackle with the problem of lifting, what we call lifting the vector potential, and then from Coulomb to potential to Yukawa potential, the electron, and then finally the what you call supersymmetry of Fermion, that's electron-electron interaction producing into producing a photon, and the reverse, which is electron emitting two photons. These are the three the three features and the differences that we emphasize in hadronic mechanics. Now, in terms of graphs, that is, how do you represent this mathematically? Visual characterization of the transition from classical Coulomb vertex, we call it, to quantum, approximately Yukawa vertex. You can see that one leads to exponential divergence, and then what we've done is to produce, to get boundedness of growth. Now, I give typical examples of typical irreversible inelastic scattering processes with current loops. I do indicate on the right, the left, the existence of the current loop, and you find this is typically represent electron, positron scattering to two photons, and the dual would be in hadronic mechanics. Proton, antiproton scattering to two photons, or proton, dual proton into two photons. And then electron proton scattering into electron plus proton resonance. It goes into E plus X. So these are what we find in the progressive characterization of the near isotopic and near admissible regimes of scattering theory are illustrated here to the left. We find projection of the McDonald's representation of the Rutherford Santilli neutron, showing its relationship to Santilli's the Torino model of the neutron. That is, Santilli features actually a neutron are being formed by electron falling onto the proton and creating a kind of current loop. Now, you find that these two processes are represented in the middle, by Lie isotopic branch of mechanics, in the Lie admissible branch. Then in the extreme right, or in geometrical terms, the fusion of two tori, electron and positron, into neutral pion. Now, this one is a characterization of the internal cube hexagon Geno-dual symmetry and the existence of the current loops near to those Geno scattering processes. I'm not going to elaborate this except to show where the current loops, how the current loops appear, and how we sketch it. You find in the red, at the lower bottom, a cube, and then with the cube and the hexagon, the proton center, and then the electron forming a loop. So basically, this is a hyperspace representation of the process. I won't go into details of this, but it shows what you call, current loop Kepler vortex system. And this is characterized by a number of points, lines, and planes, which are a cube and the vortex 7 times 6 plus pentagon, and the total is 100. Now it turns out that this may be represented by that metric tensor to the right. And if you look at the trace, One of these is 32. This is 2 to the power 5, which is the dimension of the 2 to n by 2n, representation of the of SO10. So now, basically, if you go into mathematics, the details of the mathematics, you find on the left conventional electrodynamics, and when you include the current loops, you replace the electric field by electric current, and you get the E magnetodynamics. That is the framework for account for that apparent perpetual motion that was being shown there. I'm not going to go into details, but the mathematics is available. Yeah. So let us review the deep inelastic scattering, electron proton scattering from hadronic mechanical viewpoint. This comes from the work I did with Professor Ekuma and published in African Journal of Physics of 2008. And it's referenced in the paper with Santilli. So you find the Feynman graph for A, electron point proton, which is called Mott scattering to the left, and the resonance model of deep inelastic electron proton scattering right. Now, the conventional expressions are all given here. I'm not going to read them in any detail. What's important is that what I should emphasize is the existence of two functions that are used to characterize scattering cross section, which are called the W or F1 function and the W2, UW2 or F2 functions. I think that those are details that you don't have time to elaborate, but which you can get from the details of the talk. But I should stress at this point that Professor Santilli has presented the prediction for the rest energy of particle within the scattering region. Now I give hadron mechanical expressions for the scattering cross section again. We go to what is called the Bujorken limit of infinite momentum momentum transfer and frequency, which is given in these expressions. These are corresponding points of the non-unitary, non-linear lifting transportation. And the most important point is that the functions I call F1 and F2 are now replaced by the lifted to F1, with hat and all that. So the expressions are given there, but in terms of Bujorken scale, it boils down to the graph shown where you have the this is a plot of the function and how it behaves. So it's basically a modification of, just if you remember what I said about the electron position annihilation into photon metals. Again, the details are there. You find from X going from 0 to 0.8, and then the F. And the F, these are supposed to be scale invariant functions. So let's quickly elaborate the scattering region, what I've said, and go into the details of the characterization. You will find the iso scattering and geno scattering. The schematic view basically is we assume exact validity of conventional quantum mechanics for the exterior condition when we have QM, and the validity of the covering hadronic mechanics for the interior conditions of the scattering region. And then they're generally of arbitrary shape. And then given here, but the important point is that in quantum mechanics, in the general scattering theory, we have a torus. And an important point about the torus is that there are two characteristic lengths that come in. So now these are the details corresponding to what is shown in the red there. We have two characteristic lengths representing, the way, the loop of when you cut the torus and then or the circle. So these enable us to define 4 times in what which are shown up there. Now these are the details of the Feynman graph from where you can do the calculation. For the conventional Feynman graph rules for EP scattering, the reference is given. And then you can see the elaboration of the interior in the general, the actual self-dual process, electron, positron scattering into gamma ray and the dual gamma ray. Now these are the experimental results. You can see the non-unitary genoscattering theory. The genoscattering theory. You can see comparison of the F's functions I've mentioned. The data, the source of data is stated there. And as stated above, in terms of the risk of projective variable, these are the 2 functions. I mean, the F2, for example, are given for from the calculations of Animalu and the Kuma, which is a review of deep inelasticity scattering. I don't know viewpoints, published 2008. These are the results. You can see the good agreement we had between theory and experiment, and then the F2 again. The details are given. So that basically, completes my presentation of the results and the claim that our theory of the deep inelastic scattering, EP scattering, that the near admissible and the general scattering theory formalism gives some result. So by way of discussion, which I will leave to Professor Ntile, there was in response to the question, could you please review in a language accessible to the general audience Einstein's historical prediction that quantum mechanics and therefore quantum chemistry are incomplete? So he gave the following answer, that Einstein did not accept the uncertainty of quantum mechanics, including the possibility of to identify the position of a particle with classical precision. For the reason he made his famous quote, "God does not play dice with the universe." Now, so the structure, the mathematical structure of the conventional Lie product, the Lie isotopy product and the admissible is given there. And this progressive admission has been realized in 2011 in geometrical terms at the formation of a point into a torus, characterized by the framework of the non-unitary Kevin theory, which is what presented. So I would like to make a few comments about trying to understand in a simple language as possible. So generally, trying to understand Einstein's statement verbally, gone to digital analog language and the general ASCII code. I will not go into details, but if you follow these the numerical calculations which are done practically by hand, showing how to translate what Einstein says, that wave particle, a quantum mechanics is not complete theory. You have to add, it's not complete wave particle duality theory. To have a complete, representation of that statement in a SO10 group of representation. Or alternatively, God does not play a dice with the universe, and you have to add entanglement interior. Get a complete time determinism is represented there numerically and is equivalent to Lie admissible penetration. So one of the features using this translation is that we can characterize the coronavirus. It comes to 155. And coronavirus isospin 256, which is the same as the Lie admissible penetration, same as the complete time determinism. I will not go into details. You look at the presentation and ponder. Right. Finally, I make a linguistic elaboration of API argument for the analog characterization of quantum chemistry and particle calculus. What we do again, we start to have quantum mechanics is not complete theory, 666. God does not play the dice with the universe entanglement interior, 666. Complete time determinism. Then we say scattering of two fermions into one boson has incomplete, we have to add missing particle. And is that missing particle that the admissible penetration accounts for? I think I'll say thank you for listening. I appreciate my co-presenter elaborate substantively. Thank you for the conference. Thank you for listening.